collisions as being effective or ineffective. The three factors that we talked about affecting the collision is, did you collide? Like, did you actually collide with a reactant that you're reacting with, the other reactant? So did you collide with one of the reactants? Number one. Number two, did you have enough energy, which in this case is kinetic energy? Are you going fast enough to have an impactful collision? And orientation. Did you collide in the right part of the molecule for it to actually react properly? So these factors affect whether or not you're going to have what we call an effective collision that will lead to the reaction. So you'll have no reaction if the collision, so if you collide with incorrect geometry, that's having to do with that orientation, not lining up properly, or insufficient energy to rearrange the bond. Or bonds. Okay, so the next sentence is talking about what is going to work. So it's just kind of restating that. So it's saying, okay, so if you want it to be effective, you need to make sure that your collision occurs I'm just going to fix this. All right, with the correct geometry. So the correct geometry and sufficient energy. Am I saying the same thing? Yes. It's kind of said in the positive here and then said in the negative, so that hopefully we fully understand what's required. Now here's the new part, okay? We're going to form an activated complex. So this is the new term that we're going to investigate today. An activated complex is what happens right at the moment that you get this collision. So you have your two reactants colliding. We're only going to talk about two at once, although you could have more than two, but it's unlikely. Those two are going to collide, and in the moment that they collide, they form an activated complex. We'll be coming back to this a few times. So if all the conditions are right, what is an activation energy? So we use this term activation energy only at the title of this page. Sometimes it's given as E sub A, but essentially it has to do with the minimum amount of energy that you need to start the reaction or create an activated complex. Really important that we understand it's the minimum. So you can have more, but the activation energy represents the minimum energy that you need to put in order to have a successful collision. So the reactants can, this is another key new idea, overcome the repulsive force of the external valence electrons. So I'm going to write it, and then I'm going to re-explain it again, okay, while you guys are writing. I actually mentioned this last class. It's a little bit of foreshadow, but I didn't explain it well. you go ahead and write, we're going to form an activated complex. Great. We're talking about overcoming the repulsive forces of electrons. Why is the electrons on one atom or molecule going to be repulsive to another atom or molecule? Well, they both have electrons on the outside. As a matter of fact, everything is going to have electrons on the outside. So if I have a dense positive core, that's all well and good. But it's almost like you're running around with bubbles around you, and you're going to just bounce off of each other if you have these electron clouds on the outside, and you try to come in contact and have a collision. There's repulsion, there's negative, negative, like repels, like repulsion. Basic concept. Some of you have chemistry, you'll understand a little, or physics, you'll understand a little bit better. We talk about that in physics a lot. But you know that a negative charge and a positive charge go together, two negatives don't. So this idea that we have a surrounding electron cloud creates a little bit of an electron, almost think of it like a force field, although it isn't a force field, but we could think of it that way, around those entities. So I have to be moving really quickly to kind of overcome that force. Do you ever try to force two magnets together that are not like on the wrong poles, where they don't want to go together? You can push them hard enough to push them together. So imagine if you did this, you would actually get past that outer cloud. You could break past that little bit of repulsive force, and you can cause that reaction to actually take place. New bonds to form or bonds to break. If the collision forms an activated complex, and it will only do that if you have enough energy to overcome the external repulsive force of the electrons on the outside. You probably never thought about that before. Okay, so that's just one of the main reasons that we have this activation energy. Even if the reaction is favorable, even if the overall charges were positive on one and negative on the other, there's still an electron cloud, a valence electron outside, right? Even actually all the electrons are on the outside. So that is the minimum energy required, activation energy, and why. And we'll be coming back to this later. So now we're going to do this in imagery, in pictorial form. What is the activated complex? The activated complex is high energy. It's an in-between unstable state that will undergo further changes to become the product. So it's typically not the product. It's just the first step when you have a effective collision, you're going to get this activated complex. So we'll write that definition. It has high energy, and as you know, the universe will tend towards a stable or lower energy state, which means that this is a temporary, unstable, and we use sometimes the word in between. So it's like a step in the path, but it's not a product. In between stage in a reaction. The reactants are in the process of forming or rearranging to form their bonds. So rearranging bonds to form products is what I want to say. So they have to get together, okay? This is not magical, right? This is the nitty-gritty. When you have your two H2s and an O2, so classic example, back to water, right? When you get these guys together, they can't just poof into water molecules. The first thing that needs to happen is you need to actually have an activated complex that involves your O bonded to an H2 and your other O bonded to an H2. Hands up if I can zoom in now. Excellent. Your activated complex here is going to form when these three reactants collide successfully, and then temporarily it's going to look like this. You'll be asked to tell me what the activated complex would be, what it might look like, what the formula would be based on the reactants. So what are you doing? You're just sticking these guys together. So they're going to form this activated complex briefly, and as you can probably guess, there's going to be a breaking of this double bond of oxygen here. And when that bond is broken, you now have two water molecules, all balanced and everything, like we have been learning all along. We always kind of brush over this activated complex part because, you know, it was complicated enough. We didn't tell you about it, but it was always there. So we have a formula for this activated complex, and I'm going to ask you to give the formula more often than drawing it. So what would the formula be? Do you think, you don't need to say it out loud, but what do you think the formula would be for this activated complex? Yes, correct. H4O2. There are 4 H's, there are 2 O's. That's a question that you would be likely to see. Now we're going to take those little energy diagrams that we've been studying for our grade 11 review, and we're going to make them more truthful. Instead of the graph going from higher energy to lower energy, it's actually going to go really high and then way back down, further down than we started. And so if this was in grade 11, and you're not going to write this down, but if this was in grade 11, or even your quiz next week there, it's just going to go like this. And all of this hump wouldn't be here. And your graph would just show the energy going down. And what would we call it? Exo. And so for endo, it would just start down here, and it would have just gone, don't draw this, it would have just gone up like this. That's what we were studying until now. Of course, in reality, it's more complicated. It actually requires activation energy. Both endo and exo require activation energy. So for both of these types of graph, you're going to see a big old hump, the activation energy hump. That's what I call it. What it means is I need to increase the energy here, and then once it's hit the minimum amount of energy required, the activation energy, then it will release its energy. And if it releases more energy than I put in, then it's exo. If it releases less energy than I put in, it is endo.